Hello, my name is Felipe Herrera, and this is my Physics 2211 Lab 4 Oscillation. So, introduction to this lab. Excuse me. The purpose of this lab is to observe the motion of a spring mass system with the mass oscillating. And our goal here is to determine that the model aligns with the energy principle. Determine if. So here's some key concepts and principles. So Newton's second law, an object change in momentum is proportional to the net force applied, and the energy principle, an object's change in energy is the sum of work done by the surroundings and thermal energy exchanged with the surroundings. So here's some equations that we're using. Velocity final equal velocity initial plus F net over M times delta T. RF minus R initial plus V average times delta T. K equals 1/2 mv squared. Universal gravitation equals mg delta H, or sorry, that's potential energy. And US equals 1.2 ks squared, so that's spring potential energy. So here's my tracker video. Yeah, there you go. I'm gonna let it play. So here are the computational model initial conditions. So for the ball, for the mass of the ball, I said 0.402 kilograms. And then the position vector, I said it was at negative 0.107 in the x, negative 0.632 in the y, and 0 in the z. And the ball velocity starts at 0, 0, 0. So also, I said g equals to, well, g was 9.8. The spring constant, 6.872, and the relaxed length is 0.1261 meters. So here's the computational model. So L equals the ball positioning minus the spring position. L hat equals L divided by magnitude of L. S equals magnitude of L minus L initial. K equals 0.5 ball mass times the magnitude of ball velocity times the magnitude of ball. So magnitude of ball velocity squared. And then potential energy, ball mass times gravity times ball position in the y, and spring potential energy 0.5 times ks times s squared, and E equals k plus us plus ug. So basically, yeah, the rest of it was just plugging in all the formulas for the values. So here are the results that I got. Lovely. Here we can see that the change in energy is 0, which is what we want, but I'm going to talk about that on a later slide. Here was the experiment versus the actual model on one graph in the x, and then here was it in the y. I think in the y I didn't calibrate it right, but there. Imagine if this was here, that'd be pretty good. So discussion of these results. Yeah, like I said, the energy principle is satisfied. There are no external forces that affect the isolated system. Therefore, the change in energy must be 0. And though there are different energy types in the system, the total change in energy is 0. So to wrap it up, in the x direction, this is, sorry, the oscillation periods, I didn't label it, but 3t equals 0.4874 seconds. I got that from the tracker video. T equals 1.65 seconds. K equals 4 pi squared times 0.402, which was the mass, divided by T squared. So in the x direction, I got 6.011 Newton meters, and in the y direction, I got 7.072 Newton meters doing the same calculations. Okay, here's my potential errors. So there are various potential places for human error, including my code and tracker video. This includes that my graph is not accurate for the y position on the tracker, as I may have picked the wrong origin when beginning my tracker. And I didn't notice that till it was a little bit too late, but I do apologize. So yeah, thank you for watching.